Alright, here we go. Alright, so we had finished these two boxes in the middle. And while we were waiting for the camera to load here, we talked about the Rolle's theorem yesterday, so we already reviewed that. We know that f of x has to be continuous on the interval a to b, differentiable, and f of a and b have to be the same value. Then Rolle's theorem tells us it guarantees to exist some value c in between a and b where the derivative would be equal to 0. So we need to use that definition still. That's what we're going to talk about with the next two examples here. So let's go down to number 1. For each of the functions below, determine whether Rolle's theorem is applicable or not. Then apply the theorem to find the values of c guaranteed to exist. So the first one, g of x, 9x squared minus x to the fourth on the interval from -3 to 0. So specifically, we want to think about this interval. This polynomial, since it's a polynomial here, is it continuous from -3 to 0?
Yes.
Yeah, it's going to be continuous there. Okay, so let's state that. G of x is a polynomial function, so it is continuous on -3 to 0. Okay? Is it differentiable? If we take the derivative, can we evaluate it at every value from -3 to 0? Or are we going to run into any trouble? You could even think about taking the derivative of it in your head right now. Well, eventually we're going to have to take the derivative, but if you take the derivative, can you plug any value into it from -3 to 0? I think so. It'll be differentiable. So, and differentiable on -3 to 0. So those are the first two stipulations, continuous, differentiable. Now we have to determine whether the endpoints, the -3 and the 0, are equal to the same thing to see if we can apply Rolle's theorem. So g of -3 needs to equal g of 0. Well, let's see, what is g of -3? If you plug in -3 to the original, what do you get as an answer?
0.
You get 0? What if you plug in g of 0? You get 0. So they are equal to each other. So, Rolle's theorem applies. So now that it applies, we went through, that's the definition. We know that we can use the theorem. We know there's some value c where the derivative is 0. So what's our next step now? Because we want to actually find that value of c. What's our next step? Yeah, find the derivative. We need g prime of x. G prime of x would be what? Who has the derivative? Take 18x minus 4x cubed. Okay, that's the first derivative. We want to know when the first derivative is equal to 0. So 0 equals, and I can factor out a 2x. Okay. So now I would have 2x equal to 0, so that would be x equal to 0 is one possibility. Then I set 9 minus 2x squared equal to 0. And I would get x equal to plus or minus square root of 9 over 2, which would simplify to plus or minus 3 over square root of 2. So I found three critical values, 0 and plus or minus 3 over the square root of 2. Those are my three critical values. Now think back about the interval. The interval is from -3 to 0. So which one of these is the c value that we can guarantee the derivative is 0 at that point. Let's look at it one at a time. Can this be our value? Can we guarantee that 0 is that value where the derivative is equal to 0? Well, let's think about it. If we have an interval, the interval is -3 to 0. Can you take the derivative at an endpoint and know what the tangent line is? No, at an endpoint you can't do that. You don't know where it's going after that endpoint, so you can't. So technically, it's not in the interval. Okay, so the 0 can't work. Alright, so we're from -3 to 0. Can +3 over the square root of 2 work? No, because that's greater than 0. -3 over the square root of 2, is that value between -3 and 0? Well, if you're not sure, you have a calculator. You do -3 divided by the square root of 2. You should get -2.1. So our C value, the C, where the derivative is 0, is -3 over the square root of 2. By Rolle's theorem, that's what our guaranteed C value is, and we actually found what the C value was. So we know at that point the derivative is equal to 0. Does that make sense how we used Rolle's theorem for that? Any questions before we go to the next example? Any confusion? Alright, let's look at number 2 then. So we have g of x is sine of 2x over x plus 2 on the interval from -4, -1. Okay, so let's go through Rolle's definition again. We have the stipulations that we have to follow. First one, I believe, is continuous. So on this interval, is g of x continuous?
No.
Why not? Okay, if we plug in -2, we get 0 on the bottom. That makes it undefined, so it's not continuous at all values. G of x is discontinuous at x equals -2, and that's in our interval. So Rolle's theorem doesn't apply. So at this point, now for this function, we cannot guarantee between those two values that there is some value c where the derivative is 0, because Rolle's theorem does not apply. Any questions before we move on? Alright, let's go ahead and flip over then. Or next page, actually. Alright, so it says Rolle's theorem guarantees that if a function is continuous on the closed interval a to b, differentiable on the open interval a to b, and f of a equals f of b, then there's guaranteed to exist a value of c on ab where the instantaneous rate of change is equal to 0. In other words, that means derivative. So that's the same thing as saying f prime of c equal to 0. So that's the definition we wrote on the previous page. That's the one we used the entire time. So that's just the conclusion of it before we move on to the next thing. The mean value theorem is similar. In fact, Rolle's theorem is a specific case of what is known in calculus as the mean value theorem. So another word for mean could be what? Average. Average value theorem, mean value theorem. And like yesterday, we're just going to go ahead first, copy down the definition of it, and then kind of look back at it and see if we can understand and use it. If f of x is continuous, on bracket AB, so the closed interval AB, and differentiable on the open interval AB then there is guaranteed to exist a value C on the open interval AB such that f prime of C equals, well, for Rolle's theorem it was 0. For the mean value theorem we think about the average, so it's going to be f of B minus f of A all over B minus A. You can think about that average, averaging two values. If f of x is continuous on the closed interval a to b and differentiable on the open interval a to b, then there is guaranteed to exist a value c on ab such that f prime of c is equal to f of b minus f of a over b minus a. Okay, so it's similar. We still have to be continuous. We still have to be differentiable. But it doesn't state anything here about our endpoints being the same. And they're not the same because in this case we're talking about the mean or the average. So we're going to have two different endpoints that we're taking the average of. So the derivative will be equal to the average of those two. Alright, so let's go ahead and look at the first problem beneath. Consider the function h of x equals 3 minus 5 over x. The graph of h of x is pictured below, so we see it down there. Does the mean value theorem apply on the interval -1 to 5? Explain why or why not. So from -1 to 5. So think about the problem. Here's your original. Here's the interval. There's a picture there if you want to look at the graph. Would the mean value theorem apply? Yes or no? If you're not sure, draw some lines on your graph, -1 to 5. Look at your graph. Look at your actual equation. Think about what happens when you plug values in. Just double check. So check if it's continuous. If it's continuous, then check if it's differentiable. But is it continuous from -1 to 5? Okay, I hear one no.
No.
I hear two no's. Anybody want to explain? I hear three. Daniel, go ahead.
X cannot equal 0, and 0 is on the interval -1 to 5, so it's not continuous.
Yeah, if we plug in 0, we get an undefined here for this 5 over 0. So h of x is not continuous at x equals 0, exactly where Dan told us, because h of 0 is undefined. So MVT, mean value theorem, cannot be applied. Now it's important for this problem, because they're going to be asking multiple parts, it's important to say the mean value theorem cannot be applied on, and list the interval, -1, 5. Because it's possible, if you have a different interval, that we could use it. But the interval they specifically gave us right here has the value 0 in it, and it's undefined. So we cannot use -1 to 5 as our interval. So we want to work through multiple scenarios here. So now we want to look at the next scenario. Does the mean value theorem apply on the interval 1, 5? Why or why not? So again, look at your graph, look at your original equation, think about the interval. Would this mean value theorem apply?
Yes.
Yeah, first you have to figure out, is it continuous? So you're going from 1 to 5. Well, yeah, it's continuous the whole way. Would I be able to take the derivative everywhere and get a value? Yes. So it's differentiable. So h of x is continuous on the closed interval 1 to 5 and differentiable on the open interval 1 to 5. Remember, we have to do open interval for differentiable because you can't take the derivative at the endpoint. So it's the open interval. So MVT applies, or MVT does apply. And we stated the interval up above, so we don't have to state it again. Does that make sense so far? Well, we got two different answers for these two parts. Everything must apply. Alright, let's look at the last, or this third part here. Graphically, what does the mean value theorem guarantee for the function on the interval 1, 5? Draw this on the graph to the left. So think about that. Graphically, what does the mean value theorem guarantee for the function on the interval 1, 5? So again, we're talking about 1, 5. So that from here to be here. So we already said the mean value theorem applies within that interval. Graphically, what do you think that means? Think of your definition. Go back to what the definition we wrote about it. Think of your endpoints. Think about what is actually being said here. Graphically, or if you can explain it in words, what do you think is happening? So let me ask this a little bit. If we take a derivative at some point, that's what kind of line? If we take a derivative and we know a specific point and we draw that on our graph, what does that represent? What kind of line? A tangent line. So we know if we evaluate the derivative at some certain spot, we're going to get a tangent line. Okay? But they're telling us in this definition, whatever that value c is, where the tangent line, it needs to be equal to this average. Well, the average deals with how many points? Average is how many points? If you're finding an average, you need how many points? 2. You need 2 points to find the average of those 2 points. If I draw a line through this function and it touches in 2 places, what kind of line is that? Secant line. So I know I'm going to have a secant line that goes through these 2 points. And I know it has something to deal with tangent lines too. According to the definition, what is this actually telling me then? So think about that a little bit. Tangent lines, secant lines, the definition. What are we actually figuring out? What is this value of c that we're trying to find? What's true about the tangent line and secant line? Daniel?
At a value of c, the slope of the secant line that is shown must be the same as the slope of the tangent line at that value of c.
Exactly. So they have to be the same. So in other words, they're not going to be on top of each other, but they're going to be parallel to each other. Exactly. So we know somewhere, now again, we haven't found it yet, so I'm going to say maybe it's right here. We have some value c where the tangent line to that line is parallel to the secant line. So this is a tangent line, it only touches in one spot. There's some spot c between here where the tangent line is parallel to our secant line. So in words, we need to describe this over here. A value x equals c where the tangent line at x equals c is parallel, I'm going to just use the symbol for parallel lines, is parallel to the secant line through the endpoints of the interval. So a value x equals c where the tangent line at x equals c is parallel to the secant line through the endpoints of the interval. So we drew our secant line, it was the endpoints. Somewhere in there was a c value where the tangent line is parallel to that secant line. Now that's just the idea of it. We haven't found anything yet. Are we okay with the idea, the definition, and how it applies to this? Okay, so let's actually try to find what this c value is then. So apply the mean value theorem to find the value or values of c guaranteed for h of x on the interval from the closed interval from 1 to 5. So we have the original function h of x equals 3 minus, what's another way I could write 5 over x? Might not look as nice, but what's another way I could write that? Think about the exponent it has, because it's going to make it easier to take the derivative of it. So I think I like where you're headed. And then do what with it? Yeah, bring it to the top. So it's to the first power, but if you bring something to the top, it makes it negative. So we would have 3 minus 5x to the negative first. So that's still the same thing as what they had given us. This is going to be easier to take the derivative of. Yes. Yes, you may. So the derivative, if we take h prime of x, let's just figure that out. Well, derivative of 3 goes away. What's the derivative of negative 5x to the negative first? Think about your power rolls. Who has the derivative? Joseph? 5x to the negative second. Very good. And since we took the derivative, we could rewrite that as 5 over x squared now. Okay. So we have our original function, we have the derivative. Let's find our endpoints. So we need to know the endpoints to be able to use the mean value theorem. So h of 1, that's 1, and h of 5. So we need to find those two values. You have a graph or you have the function, either way. Find your two answers. Find out what h of 1 is and what h of 5 is. Use your function or the graph. It does not matter since you have both. When somebody gets them, let me know what those two values are. Braden?
H1 is negative 2.
Okay.
H5 is 2.
Very good. So we get negative 2 and 2. Those are the values of our endpoints. Okay. So from up above, the definition, if you look back up at the definition, we know the derivative has to be equal to the average. Well, the derivative we found, that's 5 over x squared. It has to be equal to the average, so that's the f of b minus f of a over b minus a, so that's the part we're going to do now. So f of b is 2, minus negative 2 is plus 2, over 5 minus 1. Okay, a little bit of simplifying. We still have 5 over x squared equals, we get the 4 over 4, so that's 1. Now we want to get x by itself. Well, we have to multiply the x squared over. So we get 5 equals x squared. Again, we're just simplifying, trying to get x by itself. So ultimately, x is equal to plus or minus square root of 5. So we're almost there. We said there's some x value, a c value, which is an x value, in between our endpoints that would guarantee where that tangent line is parallel. Well, I got two values here. Does it make sense? Would both of these values be within that interval? No. Only one of them. Which one? Positive square root of 5. So if you want to find the decimal version of that, our C value, which is square root of 5, the positive one, is 2.236. So again, we just used the idea. We knew that the mean value theorem applied. We went through the whole scenario of that interval. We used the original and the derivative and set the derivative equal to the average of the endpoints. When you solve that, you're able to get what that x value is. And we found that x value, or C in the way of the definition, is square root of 5, or 2.2. Can't be negative square root of 5 because that's not within the interval. So that's your C value. Make sense? We feel okay with that example? Anything you need me to repeat? Go back over? Alright, so I think what we're going to do is stop there and leave the rest for Friday, for tomorrow. Alright?